Alright, welcome. Today we are talking about similar triangles once again. Notice that today we are looking at a few properties that can help us tell whether or not a pair of triangles is similar. These should look pretty familiar because they're basically the same things we were using to prove triangles congruent. The only difference is that there is no ASA or AAS. Instead, we'll just say AA. So if your two triangles have a pair or two sets of congruent angles, they must be similar. If all three corresponding sides are proportional, the triangles will be similar. And if the angles between two sets of proportional sides are congruent, then we have similar triangles. So again, angle, angle, side, 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 or side, angle, side. So let's look at this in an example. So we want to determine whether the triangles are similar. If we are looking at the picture on part A here, we'll notice that both triangles have a 57-degree angle, but the last two angles are different. So initially you might look at that and think that they're not similar because their angles don't match up. But we probably want to figure out what the missing angle is in the two triangles so that we can look at all the angles together, because it's possible that the 48 degrees for angle J is equal to the missing angle of triangle MPQ and vice versa. So what I'm going to do is take triangle LKJ, figure out the number of degrees for angle K, and see if that matches up better with triangle MPQ. So we'll add the 57 and the 48 to get 105. Subtract that from 180, and we get 75 degrees, which tells me that there has to be 75 degrees at angle K. Now all of a sudden, we do have a pair of congruent angles. Therefore, these two triangles must be similar. So we're going to make our similarity statement. We're going to say that triangle JLK is similar to triangle QMP. And to explain our reasoning, we'll just say that we used angle-angle similarity. So on part B, we don't have anything marked other than the fact that XR is parallel to TW. So we're going to have to use that fact to locate some congruent angles. If we remember from when we were doing our proofs, we're always looking for the congruent angle pairs from our parallel line activities earlier on. We know that angle R has to be congruent to angle W because those are alternate interior angles. At the same time, we notice that angle RSX has to match with angle WST because those are vertical angles. So therefore, the triangles must be similar because we have matched two pairs of congruent angles. So, triangle RSX is similar to triangle WST, and once again we used angle-angle similarity. So just like with congruent statements, the similarity statements have to match up the corresponding angles and sides, so be aware of that when you're filling these in. Let's go ahead and try guided practice 1A and B on your own. Let's look at the next example. So again, we need to determine whether or not the triangles are similar. This time we're only given sides. And in order to determine the similarity, we're going to need to look at the scale factor for all of the corresponding sides. So what I would recommend is to kind of locate the smallest side from each triangle first and set up your proportion. So if I divide 5 and 12.5, I get 0.4. So then I'm going to go and find the next two biggest sides in each triangle. So the 6 is next over here. The 15 is next over here. So if I take 6 divided by 15, I get 0.4. And I notice everything looks good so far because we're getting the same value. We need to get the same value every time. Otherwise, our scale factor doesn't match and our triangles won't end up being similar. So 8 divided by 20 gives me another 0.4. So I notice I got the same scale factor for all three sides. Therefore, my scale factor was consistent. My triangles are similar. So to write the similarity statement, we can say that triangle QRP is similar to triangle TRS. This time we used side, side, side similarity theorem. All right, part B. So this time our triangles are sort of stuck together. So I'm going to trace out my two triangles. Make it a little bit easier to see. The first thing that stands out is that angle A is in both triangles. Right, so we remember the reflexive property tells us everything is equal to itself. So we know we can use A as a sort of starting point for our two triangles. Since we don't have any other angles, we're going to have to use the scale factor between the pairs of sides. And the other thing to watch out for is that this 4 and this 5 are not side lengths of triangles. Rather, they're pieces of the missing sides for the larger triangle. So what I'm going to do is take the 8 and the 12, add them together, 8 and the 4, add them together to get 12. And that's the side length from A to C. Over here, we can take the 10 and the 5 and put them together, and they'll add up to 15. So when I'm setting my proportions, I want to use the 12 and 15 instead of the 4 and the 5. So just like last time, we'll take the two smaller sides, so 8 divided by 12. So you can either put that as 0.67 or as 2/3. If I take 10 out of 15, that is also 2/3. So I have this matching scale factor on both sides of the triangle. Therefore, triangle ABC must be similar to triangle AFE. Using side, angle, side similarity. All right, so you have a couple guided practice to try on your own. Let's look at example 3. Okay, so this time we know the triangles are similar. The directions got cut off, but let's assume that they told us the triangles are similar. We need to use the similarity to find BE and AD. Well, here's BE. I notice that's got an X. So once again, let's trace our two triangles and use our proportions to find the missing variables. So I'm going to take X over 3.5 because the X is corresponding to the 3.5. Then I'm going to take 3 over 5 because again the 3 over here corresponds to the 5 over here. And then we will solve it out by cross multiplying. So 5x equals 10.5, which means x equals 2.1. And x is the only thing on side BE, so BE is 2.1. Alright, so let's go ahead and solve for y. Remember that we want to use the entire side length of the bigger triangle, not just the two pieces. So we're going to say that y over y plus 3 is equal to 3 over 5. And then once again we will cross multiply. So 5y equals 3 times y plus 3. So 5y equals 3y plus 9. So 2y equals 9. Y is equal to 4.5. And if we're looking for that whole side length, because it told us to find AD, we're just going to plug it back in. So 4.5 plus 3 equals 7.5. So that'll be the length of AD. Alright, we have one more example to look at. And that is a mid-segment. So a mid-segment connects midpoints of opposite sides of the triangle and creates a new triangle that is half as large as the original. So if we are looking at a picture where x, y, and y, z are midpoints, and we're looking for the length of xz, I'm going to trace out my smaller triangle that's half the size of the original. So if I've got 13 here, I'll divide that in half. You get 6.5. If I am looking for ST, so ST is this. I notice I've got my mid-segment at XY. So this guy is half the size of the whole thing. So if I have 7 over there, I need 14 over here, so ST is 14. And for the final one, we are looking for angle RYX. So again, this triangle is half the size of this one. So if we notice, we have another triangle right here that completely matches. It is congruent. So whatever angle I have here has to be congruent to the obtuse angle over here. So those are both going to be 124 degrees. All right, that's all we have for today. I will see you guys next time.